All right, recording has started. All right, so I'm very pleased to announce our next keynote speakers, Guido de Croon and Bart Duisterhof. Guido was my former professor when I was still at the MEV lab for my PhD before I joined Bitcraze. And Bart is a former lab mate of mine. And they did some really cool stuff with the Crazyflie after I was gone. So only made a lot of sense to invite them for our BAM days. So Guido, the floor is yours.
Thank you. So, my apologies. My internet is not so great. I'm somewhere in the profound region of France. My apologies if it's not perfect, but I hope you can hear me. Indeed. So this talk I'm going to give together with Bart Duisterhof, and we're going to talk about fully autonomous Crazyflie swarms. And actually, I'm going to talk a little bit also about the work of Kimberly, by the way, when she was still a PhD student. But yeah, let's get started. So if people think about autonomous drones, then they typically think about relatively big ones. And what you see here is a drone performing an autonomous drone race. It was the air competition in 2019, and this drone, was provided by the organization. And I'm quite proud to say that at the time we won that race, and the $1 million prize that went with it. And that's quite a big drone, but in our lab, actually, the focus we have is on really tiny, lightweight, and agile drones. And so the drone that you're going to see now, and yeah, I guess you're going to see it pretty slowly, is the Delphi Nimble. And the Delphi Nimble flaps its wings just like insects do. And actually, the dynamics of the drone are so much like insects that we could explain some phenomena that were until now not understood by biologists. And here you see the mechanisms behind the control of the Delphi, which can make really agile maneuvers. Now, for drones, it's always important that they are restricted in terms of size, weight, and power. And if we look at the drone that was used in this drone race, and it's the kind of drone that most people are used to, but I guess, this being the crazy days, I think people are used to smaller drones. But this drone was 70 centimeters in diameter, weighed 3 kilos, and required 600 watts to fly. And it has everything on board that many roboticists dream of when they want to make autonomous drones. And so it has an NVIDIA Jetson Xavier on board, which weighs 280 grams and consumes around 30 watts. It has a GPU with many CUDA cores. It has a lot of memory, 42 gigabytes. You can run deep nets, and you can even run, fancy visual odometry or SLAM on it. And that's the kind of thing that most roboticists would like to run on their drones. Here on the right, we have the Delphi I showed you. It's 33 centimeters wingspan. It weighs only 29 grams, so it's 10 times as light as the Jetson Xavier itself. And it consumes 6 watts to fly. And if you want to make this drone autonomous, then obviously you need a smaller processor. And the kind of processor that we had on there was a microcontroller, the STM32F4, which is not very different from the kind of processor that is typically embedded on the Crazyflie. And so it's pretty lightweight, around 4 grams, consumes around 0.2 watts, has a 168 megahertz processor and only 192 kilobytes of memory, which is of course very little. And then you may wonder, is it possible to make such tiny lightweight drones autonomous? Now, in principle, the outlook is grim. Because most people, when they think about autonomous flight, they think about SLAM, simultaneous localization and mapping for navigation. And when you look at the state of the art in SLAM, then typically it requires in the order of hundreds to thousands of megabytes of memory. And so that's a lot of memory which is simply not available on such tiny drones. And if you cannot do SLAM, I mean, can you then really do complex tasks? I think many roboticists would say that that is not possible. Of course, you could think, yeah, perhaps with deep nets, instead of SLAM, if you have a deep net that's end-to-end trained, also very nice. But for that, you need, a processor like the NVIDIA Jetson, for example, which weighs 85 grams and has power requirements of around 7.5 watts. Also, that is really not possible to carry on a Delphi. And so the typical deep nets, let's say, also cannot be run on these tiny vehicles. So, is it then still possible to make tiny drones autonomous? And we think it is actually very much possible. And that's why today we're here to talk about, well, I'm going to talk a little bit about some of the things we did in our lab. And then I'm going to work towards the Crazyflie, and Bart is going to talk about the last achievement we did with these Crazyflies. And the solution in our eyes is to look at nature, because if you look at small flying insects like this fruit fly, and then they're able to do many things. So to fly, avoid obstacles, navigate, find food and shelter, interact socially with other insects, and all of this for approximately 100,000 neurons. And think about the fact that we humans have 86 billion neurons in our brain. So that's really a tiny amount of neurons, tiny number of neurons that is sufficient to do all these complex tasks. So there should be something we can learn from nature in order to make also tiny drones autonomous. Now, to illustrate the kind of solution that you find in nature, let's have a look at this dragonfly, which catches the fly. And not only can it catch flies, it does so very well. So when it goes after a prey, it catches them around 95% of the cases, which is really great because the lion, which we believe to be the king of the animal kingdom, he only catches 75% of his prey. So the dragonfly is much more effective. And what is very smart about the dragonfly is that it moves to the point where the fly is going. And so why is this smart? Well, I have small kids, and when you play football with them and you kick a ball to their side, then when the kids are very small, like 2, 3 years old, they run to where they see the ball. And what happens then is they run towards the ball, but then the ball passes them, and then they have to go back and run after the ball. But if you look at the dragonfly, it immediately flies to where the fly is going. Now, if I ask engineers to solve this, then they come with a procedure like the following. What is the velocity of the fly? Where is it moving to? What should my own velocity be to get there at the right time? And preferably having a model of their body to then calculate how to get there exactly at the right time. Now, you may imagine that this procedure, if you want to embed it in programming, is actually pretty complex. And if we ask biologists what dragonflies do, then they come with the following rule. Let's keep that small moving thing in the same place in my image. And so they detect the fly and they try to make the fly bigger while keeping it in the same place. If they do so, then they catch up with the fly exactly at the point where the fly is moving to. And so you can have this complex task, and you can try to take that complexity and represent it in your program, which robotics is often doing, or you can try to find a simple solution to such a complex task. And that is typically what nature is doing. And that's also what we want to do with our robots. Now, you may say, okay, Guido, there's more difficult tasks, like, for example, odor sensing. And when you have these fruit flies, they always sit on your fruit. So how do they find that fruit? Well, mainly because of odor source finding. And so what they do is they actually then link together simple behaviors in a smart way. So if there's wind coming from here, then the fly is going to fly orthogonal to the wind. If it smells the odor, it goes upwind. And so the orthogonal flying is called casting. And then when it smells the strawberry in this case, it's going to go upwind. And this is called surging. And when it loses the scent again, it's going to go orthogonal again. And we can see that actually in this time-lapse image here by Floris van Breugel. The fly is going up and down, it smells it, it goes upwind, it loses it, it goes up and down again, and then it smells it and it arrives at the location. Now, we embedded this kind of intelligence in multiple robots. One is the 20-gram Delphi Explorer, which is still the lightest autonomous drone today. It has a 4-gram onboard stereo vision system. And so it has 2 cameras that you can see on the side here. I don't know if my mouse is still visible. I don't see it. Oh, okay. Okay, whatever. Here it is. Perhaps I have a laser pointer. Yeah, okay. So here we have one camera. Here we have the other one. And here we have again an STM microcontroller that uses the combined images to do stereo vision to see distances. So this robot has a very small, lightweight onboard stereo vision system with which it can see distances, and it runs a small finite state machine where the states are behaviors like flying straight or turning right, and then it transitions between these simple behaviors in a smart way. And what it's actually trying to do is depicted here on the right. We have the Delphi here, and you have to understand that this version of the Delphi cannot hover. So normally, if you do obstacle avoidance and you have a quad rotor, you see an obstacle, you say, okay, let's hover, and then we turn and then we go somewhere else. But this drone always had to keep flying forward. And so it needed to have space for that. And that's why this Delphi keeps this droplet-shaped region in front of it free of obstacles, so that it can fly within its field of view and then circle in front of the obstacle to find a new direction. And this actually ensured that it would never touch an obstacle. And this actually worked very, very well in reality. And we demonstrated it in many places that we never visited before. This is a little video of the drone. Uh, Unfortunately, during the testing, we found out that apparently my videos are not very good. Fly here, and it's flying in our natural habitat, which for us is, of course, a lecture room. It's actually quite a difficult space because it doesn't have a lot of texture. So besides stereo vision, we were actually also running additional visual algorithms to detect when the amount of texture got very low, and which was also dangerous for the Delphi. And we speed it up because actually obstacle avoidance is less fun if it's actually working. And this drone could keep its height with a pressure meter and avoid obstacles as long as its battery lasted. And these are the images, which, as you can see, are very small. So let's talk a bit about swarming, because this is also something that we started to think of immediately when we had this single Delphi avoiding obstacles. We thought, okay, it would be cool to have them explore a building doing that in a group. But if you have such a lightweight drone and you want them to at least avoid the others or coordinate with other robots, how will it even know where the other ones are? And this is very important in swarming. It's actually the basis for all swarming algorithms. It says, okay, I know where my neighbors are, and then I'm going to coordinate with them. But this was an unsolved problem when we started. And of course, I think, I guess many of you know, swarm shows, so drone shows with many drones. They call them swarms, but typically these drones actually they follow a predetermined GPS trajectory. And we wanted our drones to explore unknown indoor spaces without GPS, without pre-knowledge, and really knowing where the other ones are. Because if one of these drones has a wrong coordinate, it will fly into the other, and it will not even know it's doing so because it's just following a GPS track. So where are the other drones? We looked at the literature. There was some work on infrared, very early work, so groundbreaking in a sense. But if you use infrared, that may work very nicely for ground robots. But flying robots can be anywhere in 3D around each other. And then it becomes very bulky and power hungry to do so. Another obvious solution is vision. We're actually also working on this and other groups also. It's of course a nice option. And if you look at animals like also birds, they of course use vision. But the problem for tiny robots is that the cameras are typically have a limited field of view, have a low resolution, while the other drones they need to see are also small. So that's very hard. And if you want to do vision well, you typically need quite some processing, which is not really available on board typically. So vision is very promising, but was one bridge too far when we started this. Audio, also a great idea. I think also in nature, birds use hearing and they shout to each other, perhaps even when somebody gets too close to them or something. But so audio is an option, but it's very difficult on tiny drones because they make a lot of noise themselves. The bad thing is that not only do they make a lot of noise themselves, but the other ones are the same kind of drones, so they make the same noise. So that's very hard. Now, what you see in the literature a lot is outdoors. The drones have GPS, all of them, and they just communicate their coordinates to each other. You can do this indoor if they have SLAM, for example, and they have a common map, then they can also communicate their coordinates to each other. But yeah, GPS is not always available, especially indoors. And if you want to do it indoors, then you need SLAM again, which I just told you we cannot have on these tiny drones. So what we focused on in the end is signal strength, because all drones typically have a communication chip. And when you take your mobile phone, you can see the stripes of your Wi-Fi, for example. If you get closer to the Wi-Fi, you see more stripes. And the signal strength is a measure of distance, and you can use that to detect other drones. And so we investigated this option. We were the first one to do so for drones. It requires no extra hardware. It's low power, omnidirectional, and computationally very cheap. There is a difficulty as well is how to scale this. To how many drones can you scale this? And one problem is interference because they're talking in similar channels. And so how many drones can use this in the same time? And there may also be signals that are blocking this. And so in a sense, there are issues with this. In the same way, I would like to say that vision and audio are most promising for the future because they're probably more scalable. But yeah, we have the problems that I just mentioned. Now, how did we use signal strength? Signal strength only gives you a distance. So if we have two drones that are shown here, then the strength kind of tells us the distance. But this only puts the other drone on actually a sphere around the other drone. But here I'm showing it in 2D. So on a circle around the other drone. So how is it going to find out where exactly this other drone is? So this actually work we did in 2015 and 16, but it was published very late in 2018. It was put on the archive in 16 already. So what do? They communicate their velocity, robot's body velocity, and the heading to each other. And by communicating this, you can actually find out over time where the other one is. In order to see this, suppose that I am hovering, and one drone is saying I'm moving to the front, to the east. And you see that the distance is getting smaller, and then I know that it's to my west. You know what I mean? So because it's getting closer to me, it says I'm traveling east, and then it has to be to my west, right? So that's just to give you some intuition how this works, but it allows the drones to actually exactly locate the other drone. And so this gives a solution. And what we see here is a video. We were using Bluetooth at the time, which is the worst thing to use, by the way. And so it was very noisy, but it was actually enough for a group of 3 AR drones to fly in a very close space. And what you hopefully see here, but perhaps not, because we were putting this on at the time. It was Lady Bugs, I think, was the name of the drone. Tiny drones, a bit like Crazyflies, but much less stable. And we were putting Bluetooth on them, and they were flying in a 2 by 2 meter space and avoiding each other. And so that worked. And now actually we kind of continued this development with Shushuai Lee, for example, who and together with Kimberly and Mario Coppola, so lots of people, and we made this code available for the Crazyflie as well. So you can use ultra wideband, and you use this scheme that we introduced at the time to actually localize the other drones around you, and it requires very little processing. And actually, the latest results we got, we can scale up until 15 drones quite easily. So we finally had a scheme with which we could localize other drones. But then the problem, and that's a bit the elephant in the room, was how to do the navigation. Because SLAM is, of course, important and can be used for obstacle avoidance. But the main use of SLAM is, of course, to navigate from A to B. And how are you going to solve that with so little memory and so little processing? Well, for that, we had a look at bug algorithms. And what are bug algorithms? It's actually something that comes from the area of math, let's say, in which they had agents that needed to go from a start to a target location, and they didn't have a map. But they did have their position in the world and the direction to the target. And so at the start, it thinks, okay, I should go there. then it sees an obstacle, and what it's going to do is it's going to try to get around the obstacle. And we call this wall following in bug algorithms. And then when it sees that the direction to the target is free again, it's going to travel to the target, but it sees another obstacle. And in this case, it makes the choice, for example, to go left always. So perhaps it would have been better to do this, if you had the map. But this agent doesn't have a map, so it's going to do wall following again. It sees that the direction to the target is free again, wall following. And by doing this, in the end, it actually arrives at the target. So these bug algorithms are maze-solving algorithms that are very attractive to Crazyflie-like robots because they require no map, and typically they don't even use any memory, and so nothing almost. And so that's very attractive. And the only problem that we found when we started looking at this is that, they always know where they are and where the target is, and that gives the direction to the target. Via backdoor, you actually still need a map, right? Because how do you else know where you are and where the target is? So we had a look at this, we had a look at the literature, and there's all kinds of algorithms, bug algorithms, COM1, Bug2, ELK1, ELK2, beautiful names, very descriptive. And what we did was, we first we said, okay, let's say that we know that the start location is 0, 0, and you need to go to an end location at 10, 10. And instead of a map, we just use odometry. So odometry is you keep track of your own position by just integrating what you think you did. For example, if you have a driving robot, it's the wheel encoders that tell you how often the wheel spinned, then you know where you are. And so if this odometry is perfect, then ELK2, for example, arrives at the goal in 95% of the cases. But in reality, odometry is never perfect. And that's why we introduce some noise into it. When we do that, we get a huge drop in performance. And the best algorithm goes from 95% to 30%, which is not so great. And so how can we make a bug algorithm that doesn't use this perfect odometry?
Multiple robots fly off in different directions. Instead of mapping the environment, they deal with obstacles on the fly. When their batteries are at 60%, the robots fly back to a radio beacon at the ground station, again avoiding obstacles and each other.
Okay, I didn't know this video still had the sound, but okay. So here we have a small swarm of 3 drones, and what we invented is a swarm gradient bug algorithm. And so the swarm needs to explore this space, and initially they all get their own preferred direction that makes them split up, because you want to explore it. And so this one wants to go there, that one wants to go to the top, for example, or here to the top right, I don't know, and this one wants to go there. And then they start flying and following walls. And in principle, for exploration, you don't have a specific target. You just want to fly in a direction and keep on going. But then when their battery is almost finished, they need to come back to the initial location. And we did that with a beacon, a radio beacon at the ground station. And the drones, while they fly around, they determine the gradient of the signal strength to this beacon at the base station. And they try to go up gradient. And they don't have a map, so what can happen, and you see that here, is that the purple one, it thinks, this is the best way to go to the base station. Perhaps it was, but there's a wall here, so then it has to deal with that by going around it. And so in some ways, it's a bit less efficient in terms of the kind of path that you find. It's definitely not optimal, but this kind of algorithm now allows even tiny drones to perform very complex tasks. And so, the swarm aspect is that we have multiple robots, and the gradient refers to the way in which they get back to the home beacon. So for this, we used the Crazyflie because it was much more stable and better supported than our own drones at the time. And what I'm going to show you here is the real-world tests. So we actually have Kimberly here, who was brave enough to go on an empty floor in our building of aerospace engineering. And she was there for around a month or so to develop this and do all the experiments. We have 6 drones. We put circles around them because else you don't see them. They're so small. Here we have one entering a room, and we actually have a top view here. This we made after the fact, so that you can see where they're flying. And number 2 is very close to the camera here. And we see it here, it goes into the room there. And so they spread out, they go into these rooms, and yeah, here we were using them to explore this full hallway as quickly as possible. And I think this one is going back and is going to land now. And here the two of them are avoiding each other. And so they're using again the signal to avoid each other. Here we were not having them localize each other with high precision. Here we were just using, okay, somebody is close, and the one with the lowest priority had then to get away from the wall. And we see a drone here that's visiting a room. And yeah, it visited the room. It should have gone out, but yeah, something happens and it just flies around a second time. It's a kind of random behavior that we see in our swarms. But, you know, sometimes it's good because it gives some redundancy as well. And here we have drone 4. It actually goes back to the base station and then it lands at the base station. So we did many tests. Yeah, and you see within a few minutes they explore a full floor. And if you have a bigger building, you can. And if you send in more drones, so here we have the number of robots, then you see that the coverage goes up. That's the dark blue bar. And we see that the coverage per agent goes down a bit. And what you see is that, yeah, if you put more drones, of course, the coverage goes up, but there is a limit, of course. So this in the end will, you know, converge to some value. And it's the law of diminishing returns. Now, again, also in this case, this whole algorithm, this bug algorithm, and everything that it entails, following walls, avoiding others, etc., was implemented in quite a simple finite state machine, which ran easily and at very high frequency on board of our drones. Now, that actually leads we were set it's best to probably have a small break here to give you a break. But after the break, Bart is going to continue on what I think is the most exciting thing we've done until now, the super complex task of gas source localization.
Do we want a small break?
I don't know where I hear.
Hey, sorry. Bart, can you hear me?
Yeah, I can hear you. Can you hear me?
Yes, I can hear you. Yeah, the Guido sound was going through your microphone, so that's why that was what Guido was hearing. Yeah, let's see if we have any questions, perhaps for Guido. Maybe now is the time to ask them before we continue. So you can use the chat right here. So you can ask him, yeah, what you would like to know. Of course, yeah, I've you've shown a lot of my my work there already. So
you should actually ask Kimberly.
Yeah, maybe you should ask me. Yeah, so actually, I don't really have that many questions then because it's already my work. But I guess maybe like in terms of the Crazyflie, because you guys have really adopted it. What are things in swarming with the Crazyflie that can still be improved, you would say, in order to make your research a little bit easier? So this morning we had a panel discussion with Wolfgang Honig and one guy here at Bitgrace, Jonas, and they were kind of discussing like how to use that. But that was more that's of course for the centralized. Now, well, they also said that they were able to decentralize. But what could be things that could be improved by the ecosystem that are the Bitgrace ecosystem in terms of swarm management or
Yeah, sorry. When you asked the question, I only heard easier.
Okay, okay.
It's so bad that. And so,
Yeah,
is the
okay.
question, what should be improved in the Bitgrace ecosystem for swarming, or what?
Yeah, exactly. Yeah, but something like that. But I actually see that there is a quite 2 questions, so I'll just give them questions in the chat. So
Yeah. So
let's go let's go for those first.
okay.
There is a question about what would it take to use to take. What would it take to swarm using the Delphi? That's maybe an interesting one, indeed.
Yeah, I think it's funny because the second question by Mathieu is, do you plan to combine the work done with the flapping wing drones? So we're actually
Yes.
working on that exactly now. Yeah, I mean, Delphis are more challenging than the the Crazyflies. But luckily, there's a spin-off now called Flapper Drones, which, by the way, Mathieu is running, which are more stable and actually use the exact same autopilot as Bitcraze does. So we're working with that at the moment. But what is more challenging with the flapping wings is that they don't. The quad rotors, you typically fly a bit like this in terms of attitude. But the Delphi, I don't know if you saw the maneuvers, but it's doing all kinds of stuff. And so you cannot just simply put like a downward-looking camera with a little velocity from that, for example. And so estimating the velocities of these vehicles is something we still need to do. Also, mounting sensors for obstacle avoidance. And then these velocities are mostly important if you want to use the same kind of wireless ranging and localization that I showed in the talk. And so these are all challenges, and actually we were working on them now. I think actually Mathieu should know. But yeah, so that's perhaps the wing guy, but yeah.
Mhm.
And yeah, as to your question, Kimberly, flies are great to work with. I think if we want to make them more autonomous, I didn't go into that yet, but yeah, we need perception to go to the next level, because the laser ranger deck is nice, but it's nice for demonstrations. But as soon as you come into a real world environment with plants and wires and like Bart's room there is actually pretty okay. It's pretty empty. Bart, it's good for the Crazyflie.
Just for this presentation.
Yeah, thank you.
Yes.
But in normal real world environments, you would need vision. And
Yeah.
okay, my internet is gone, I think. But you would need vision, and that's why the AI deck is interesting. But yeah, we would like, compared to the AI deck, we would like a broader field of view. Ideally, we would want omnidirectional vision as well on the Crazyflies. So I don't know if we can give a list of features we would like, but lightweight omnidirectional vision is very high on my list, with a low resolution sensor that is high frequency. Basically what insects have. So yeah.
All right. Wait, is Tobias listening? No. Yes. We'll take a note of that. Indeed, we had a lot of good pointers of yesterday when we were talking with some AI deck people as well. Well, yesterday was our AI deck day. All right. Cool. I think it's yeah, it's probably good time to switch over to Bart, over all the way in the US. So yeah, go for it.
Thanks, Kimberly. Let's see if I can share the screen. Yeah.
Don't forget to also share your camera.
Yeah, I'm going to do that now. You can see me again now, right?
Yes.
Okay. Okay, then I think we're ready to go. So thanks for the introduction, Kimberly and Guido. It's actually a project that's very related to the last work that Guido showed, where the Crazyflies were exploring the floor of a building. And this work, we wanted to see if they can localize a gas source. So why would you want to localize a gas source? That's a very interesting question. So it turns out that there's different use cases in industry and other places. So it could be that there's a dangerous gas leak in a building, but also many times there's gas leaks in industrial plants. So what happens now is there's a human that goes in with like a pretty large gas meter, and they will try to understand where it's coming from. But of course, this is dangerous and it takes time. So there's financial and hazardous incentive there, and also a chemical attached to an application. So wouldn't it be great if a swarm of Crazyflies could go in there, and we just localize the gas source and get over with it as soon as possible. So quick and in a safe way. So it's actually very hard to localize a gas source, even if you would have to, or if you would allow yourself to use a very large system. So we would need to do navigation in unknown color GPS environment, which is very hard, as Guido explained just now, and it's computationally expensive. Now we also want to do gas seeking, which is something insects and other animals are surprisingly good at, even like, your dog, for example. But they have very high quality sensors, especially compared to the sensors that we will be able to put onto Crazyflie. So that's basically where the challenges come from. In this work, we show that we should first swarm a fully autonomous and collaborative gas-seeking nanocopters. So using ultra-wideband and this relative localization that Guido just talked about, we allow them to collaborate because they're communicating states and gas readings. We use that in a novel bug algorithm. So a set of simple rules that uses extremely little resources and uses evolved parameters. And we show that it works in the real world. And we also contribute and open source today a pipeline for end-to-end environment generation and gas dispersion modeling. So if you want to evolve the parameters of an algorithm for gas source localization, it's very important to have a large variety of environments, as I'll show later. And up to now, there wasn't a really easy way to easily do that. So that's where this pipeline comes in. The content of today is related work, methodology, results, and conclusion. From a related work perspective, most algorithms that have been contributed in this space are either bio-inspired, probabilistic, multi-agent specific, or learning-based. In the bio-inspired sphere, as Guido explained, most works contributed a simple finite state machine that mimics the behavior of insects. So indeed, there's this search cast algorithm where the wind comes from here, and the animals are trying to fly upwind while staying into the plume. So every time they lose the plume, they'll start flying orthogonally to the wind direction, and once they find it, they move towards the wind. So sort of this principle of the gas must be coming from upwind. They're using that to fly, basically. These algorithms are inspired by animals like silkworm moths, dung beetles, lobsters, and even bacteria in some cases. There's a really popular line of work called probabilistic estimates, and it's actually really interesting what Guido just explained about the trying to capture the complexity of reality or trying to find some sort of heuristic that optimizes for this complex reality. And I think this is an example of trying to model the complex reality. So what these things, what these probabilistic methods do is they try to remember what they've seen before. So they've seen peaks in gas concentration. And if you also measure wind direction, you can come up with some sort of source likelihood estimate map. This is computationally expensive. Another problem is that it works well without obstacles, but our expectation is that it will not work well with a lot of obstacles where the wind direction changes and it's not possible to sense that wind direction in the wind. And there's some other methods. People have come up with formation swarming, particle swarm optimization, and even some learning-based methods. The learning-based methods are pretty limited. There's good examples of them working in simulation, but again, there's very few environments available. So it's hard to say how well they would work in the real world. And there's just very limited work in the real world with learning-based solutions. This is unfortunately a trend with gas first localization in general. Most real-world experiments are pretty limited because it's just very hard to measure this in the real world. It's kind of annoying to add the gas source to a room and to let them seek it autonomously. So in many cases, if my cursor is visible, they'll do something like a virtual source or simulation, which is of course very understandable. But we think that it's important to try to start trying these algorithms in the real world as well to see if they really work. Because in this case, people are testing a gas source in a super tiny environment, which we're not sure if the algorithms will also scale to larger environments. This is why we want to test it in large environments as well. Another concern is that the conditions in gas source localization dramatically change the task. So this is an environment that we generated. It's one of the environments that we used to train our algorithm. And this is a figure out of an old paper of Guido, where this is a way different source with way more turbulence, way more wind. And you could easily see that it would be a way different task to find this source or the upper source. And this would be more of an exploration task. This would be more of a, especially if you would be starting here, it would be more of a true gas seeking task. Here's another example of some pretty impressive literature. The authors here also use a Crazyflie, and they implemented they used an animal sensor, I think, and they also implemented an animal strategy where they indeed follow the wind direction. Again, it's very hard to say how well these things scale to larger environments when there's actually walls and rooms. It's just a very hard navigation challenge. We'll now go over the methodology and system design, simulation pipeline, and algorithm design. For the system, we use a bit-based Crazyflie. We start off with a down-facing optic flow sensor. We use this for some form of odometry and tracking waypoints, basically. Additionally, we use the multi-rangers for obstacle avoidance. And then we have a custom gas stack. Here at number 1, there's the gas sensor, which is incredibly small. It also produces quite some noise, so there's work to be done there, I think, as well. And then this is the ultra-wideband module, which allows us to sense relative range. Total weight is 38 grams, so I think it's about 8 grams heavier than the normal configuration. For simulation pipeline, I'll go over it in 2 parts. AutoGDM stands for Automatic Gas Dispersion Modeling, which means that we created this tool which can generate a large number of environments more easily. It draws upon previous tools, but it combines them into a nice pipeline. And then there's Formulator. It basically takes these inputs, so the gas concentrations, and it's a super efficient 2D simulator which we use to train and learn the parameters of our Bart algorithm. The objective of AutoGDM was the effortless generation of a large number of environments. We saw how different articles use different gas environments and gas conditions, and we think that it's important to sort of standardize these a little bit to make it easier to test different environments. That makes it easier to gain more insight into what algorithms work in which cases. This is an existing gas dispersion modeling tool. How this works is, how you can think of it is, gas dispersion modeling in high fidelity works by modeling a wind field in 3D space. So given a room, you will model a wind flow field, so vectors in 3D space, and then release particles in that space. And these particles expand sort of randomly over time. And with that information, with these expanding filaments, we can come up with some estimate of gas concentration. This seems to be one of the more accurate methods in literature to do this. Unfortunately, Cabin, which is a super nice ROS package, only automates this release of particles, but you would have to deliver the wind flow data out of a computational solver, computational fluid dynamics, and a computer-aided design model of the environment yourself. So this is basically the part that we aimed to automate here. This is an example of how it, to give you a bit more intuition on how this works. So this is what Guido is doing. So given this environment, you give it the wind flow field, and then it starts releasing these particles and get a somewhat accurate representation of how much gas is present at every point in space. This is the pipeline of AutoGDM. So we first do environment generation using some tool that actually Delphi Explorer, and then we make this sort of CAD model out of it, mesh it, and put it into a computational solver. So this is the output. I'll go over it more just now. This is the running environment generator. as I mentioned before, it's super important to have a large number of environments that is representative for what we would want to solve in the real world. So this environment generator that was contributed in this work is very useful. It can there's a number of parameters that can be changed, like number of rooms, number of obstacles, or at least obstacle density, I think. And in that way, it's useful because you can train for different scenarios. We can use some tools to make a 3D model out of it. So we basically extrude into 2.5D space. So we start with this top view that's created by the random environment generator, and we extrude it into 2.5D space. I think a cool future in the future would be to have like a randomly spawned 3D objects, so maybe like chairs or other things. And one more thing to realize is that let's say we would spawn a gas source in a closed room, and we would then spawn a robot in another room. Then that could completely mess up our evolution. So we use some OpenCV functions to detect the largest volume and come up with this sort of flow volume in our testing area, which is then like a pretty odd genuine space. For computational fluid dynamics, so now that we've created this environment, we have time to create the wind flow field. So again, these are 3D flow vectors in 3D space at every point at a certain resolution. And what it needs is an inlet and an outlet condition. So what this means is basically in your home, you would notice there's very significant wind if you would open two windows very close to each other. So this is basically the point where the wind comes in and where the wind goes out. And you can actually see like what's plotted in this figure is the magnitude or the norm of those velocity vectors. So close to edges, you would see more higher velocities, and when it's very far away from any inlet or outlet, you don't really see any velocities because the wind's flowing like this. Then there's another interesting problem, and again, this is sort of we've tried to make a first version of a fully automated gas dispersion modeling tool, and we think like it would be great to see alternatives to what we propose here. But we figured that it's important to place a source somewhere where it has the potential to be properly dispersed through the room. So imagine if we would place the source here, where there's no wind whatsoever, then it becomes much more of an exploration task than a gas source localization task. And maybe sometimes that, like in some environments, that's okay. But if it happens too often, we may end up not learning to seek a gas source, but just to explore the room. So we wanted to learn the parameters of this bug algorithm and learn to find a gas source. So we needed to place the source in the right spot. So we ended up dividing the environment in quadrants, and in this case, the centroid of the outlet is in this quadrant. So we place the source in the opposite quadrant. Again, I think you could also probably place it just at the centroid of the inlet or something, but this seemed to work pretty well for us. And yeah, the result of AutoGDM is that like after we feed these wind factors into Gadem, into the open source package, it's a ROS package. It seems like we have a wide variety of environments. So this is super easy because it has few obstacles, and the source is pretty easy to detect. And this is super hard. Like imagine detecting such a sharp wall with just laser rangers. And then there's also local optima, which is overall a pretty significant challenge in gas source localization. So imagine large magnitudes of wind, and then all of a sudden the wind dropping. This would mean that there could be pockets of gas, basically. You see that happening here, making it super challenging. So from our observations, it seems like AutoGDM is successful in generating a wide variety of different environments. And since today, for this presentation, we've open sourced or made it ready in open sourced AutoGDM. So it's available now at this link. This link will be repeated in the last slide. But please reach out to us if there's any problems, if you encounter anything, or if you have any suggestions. Please reach out for technical details to me. I will be able to help most quickly. So then, now that we have created um, this this gas map basically, and we use it in like we created a gas concentration map in 3D space, but for this purpose, for this project, we have chosen to limit the problem to 2D space. So we basically get this slice of 2D gas concentrations, and we then feed it into Formulator. Formulator is a super efficient 2D simulator that was contributed by Mario, also from FUP, and it's important for it to be efficient and parallel so that we can efficiently train our parameters. And Formulator does just that. It doesn't do all the rendering that something like AirSim would do. And because of that, it's able to train our model in a matter of hours instead of a matter of days. And this is, I guess, an interesting discussion for learning algorithms and simulators in general. I think for many Crazyflie applications where just multi-rangers are used, it's very useful to use something like Formulator because it's just so fast. One of the reasons it's so fast is that once you limit an environment or once you can describe an environment by a number of lines, it's very easy to construct things like collisions or to compute things like collisions and laser rangers. So if you look at these laser rangers, which are the green lines, it's basically just computing intersections of lines, which is super quick. Yeah, so that's a tool that we use for the for the evolution of the parameters of our algorithm. For algorithm design, like when I started thinking about the algorithm for this system, I thought it would be somewhat straightforward because it's just a number of rules. So if you haven't consciously tried to design some of these rules, it may seem trivial, but it turns out that with such limited perception, it's actually really hard to not let it crash into things all the time. So it needs to avoid other agents, other obstacles, and collaborate to find the source. So it uses these estimates, relative ranging estimates, and the source findings of other agents to find the source together, and run within the tight resource constraints of the bug factor. Some of the most promising attempts are the work contributed by Kimberly, the work that Guido showed. Then there's this other work that showed that an optimization strategy called particle swarm optimization can be used to find gas source in the real world. The only the main difference here is that their navigation strategy is using LiDAR and GPS, but it would never fit on the Crazyflie. Not now, at least. Our solution is SniffyBug, which is a name for the bug algorithm we developed. It's a novel particle swarm optimization algorithm for gas source localization using default parameters. It generates waypoints in its own reference frame to track, and it tracks those waypoints using the novel bug algorithm. So let's start with the waypoints. The idea is that the agent has a current belief state, like the current odometry of where it is in its own reference frame. So starting from the takeoff position, it has this sort of estimate of where it is. And it computes a goal waypoint in that same reference frame and it tries to go there. Of course, it's not this easy. There's obstacles and other agents in the way, but that's roughly the idea. It stops like trying to track a waypoint when it reaches within a certain distance of the waypoint. When it tries to reach it for a time that's longer than this time waypoint seconds in seconds, or when one of the agents smells something better than anyone has seen before. So imagine this: you're looking for this bottle of alcohol with a group of friends, and one of you smells alcohol all of a sudden. So then you all may change your decision. So that's sort of the intuition behind it. One of the members in this farm smells something that's better than that anyone has seen before. We all reconsider our decisions. So how do we decide where the next waypoint is going to be? There's two phases. The first is an exploring stage. When none of the members has sensed any gas, we promote exploring, because like trying to optimize for a gas concentration when the concentrations are really low is basically trying to find noise. These tiny gas sensors will tell you there's something, but it's basically noise and drift. So once it gets over a threshold of actually sensing gas, we do seeking. We go into the seeking stage when We use particle swarm optimization to try and find the highest gas concentration. So this is a nice GIF that shows particle swarm optimization. It's a population-based search method, and one of the nice properties is that it doesn't necessarily directly converge towards the local optimum. So each agent makes its own decision, and it's sort of this random weighted sum of its own best to see position, so the best gas concentration and that position that it's seen in that run, and the best seen position of the entire swarm. And that's sort of this weighted average of swarm best seen position and its own best seen position, which is why some of them will keep hanging out here. Now we get to waypoint tracking. Getting back to our configuration, we only have these 4 laser rangers, and it's a challenge to not wonder two things basically. So we also want to keep constant yaw for this horizon measurement to be even more accurate, and we need to avoid other agents and obstacles simultaneously. So we came up with these 3 states in SniffyBug. We have line following, wall following, and attraction repulsion swarming. Line following is used when no other agents are present. So let's say that this is the goal waypoint. This is the top view of the Crazyflie. We will move only in positive x and y. So basically in the directions of the laser ranger, and sort of use the zigzag pattern to get to the goal waypoint. The reason we don't just move into this direction to the waypoint is that the laser rangers are pointing in this direction, and as it turns out, it may seem like it will sense obstacles, but it turns out that especially slimmer obstacles will just be completely disregarded. So it's important to keep flying in the direction of the laser rangers for more safety. So what if there's an obstacle nearby? We use this wall following, but now to keep flying in the direction of the laser rangers and to keep yaw constant for a more accurate horizon estimate, we perform this sort of zigzag pattern around the obstacle. Finally, there's attraction repulsion swarming. It gets much more complicated once you get other agents close, because now all of a sudden there's walls and agents at the same time, which it needs to be able to handle. What we do here is attraction repulsion swarming, which means that there's a repulsive force internally applied to each agent, and there's a repulsive force from each wall and each other agent. And then there's an attractive force to the goal waypoint. We then optimize the parameters in evolutionary optimization. So parameters could be like, at what distance do we start avoiding walls? At what distance do we start avoiding other agents? Turns out that there's a total of 13 parameters in the algorithm, and we optimize those using an evolutionary optimization. The cost of each agent is the average distance to the source. So it promotes getting to the source as quickly as possible. And then we make it a bit more cautious by adding a penalty for collision. So, in theory, it should figure this out on its own, because it's not very optimal to collide and not see the source. But we force the agents to be more careful, basically, with this collision penalty. We will evolve all parameters in this case, but we'll also compare it to manual parameters. So later on, I'll show plots where we compare something that we constructed ourselves in the cybers or in our flight arena without seeing the evolutionary parameters, and then compare it to what the evolution came up with. Then there's one more thing to discuss, which I think is an interesting problem. At the time it was just a frustrating problem, but now it's a very interesting problem. It's a hard instance problem. So in this evolutionary optimization, we show it all of these environments, a total of 100 environments actually, and then we see which genomes basically perform best on all of the 100 environments. But what could happen is that it learns to perform best on average on all of those environments, because we're trying to find the agents that perform best on all of these, right? But there could be some behavior that's more optimal on average, but doesn't really work in the harder cases of these. So what we do is we use something like doping, and the intuition behind this is that let's say you're studying for a French test, and there's 80% of the words you know at some point, So you start focusing more on the harder ones. And basically the exact same strategy holds for doping. This is I thought like this is taken at the end of the evolution, and here on the x-axis is the probability that each environment is presented in each evolution, or in each draw in each evolution. So on the right should be more challenging environments, and it actually seems to be kind of intuitive. So this environment is the environment that we showed before, because of very low probability, it's all the way here. But these environments seem way, way harder with more obstacles and local optima actually. So again, basically what we're doing is trying to find the harder environments and focusing on them more later on in the evolution. The results, we finally can get to the results in simulation and in reality. This is just the training results. We train on 100 randomly selected environments, and we use the size of 10 by 10 meters because it's the same size of our flight arena. We use 3 agents in both simulation and flight tests. So what do we get? This is a simulation evaluation. So we're going to get the manual parameters and the evolved parameters. Let's first start off with the baselines that we use. So far, I've presented the Bart swarm optimization as our only reality, basically. But in fact, we also tried animatexis and chemotexis. So animatexis means that it uses some form of wind seeking, just like insects. And chemotexis is that it's using some form of chemical gradient finding. The only thing to consider here is that in reality, probably we will not be able to get these parameters as accurately as we have fed them into these models. But even then, the models that we've chosen with particle swarm optimization with doping outperform sellers. Here you can see the doping parameters outperforming manual parameters. And this is how it looks like in simulation. I think I may have received a message. I just need 1 more minute. So we also do flight testing. So we use a kind of alcohol with some alcohol in here, and we disperse it through the room, and we use it in a 10 by 10 meter arena, and we test in 4 different environments. And the goal was to see, does this really work in the real world? So this is like I hope you can see the Crazyflies here. They're these small blue dots, and we try to create environments that are challenging. So they have walls and obstacles and relatively really challenging environments. This is basically how it looks like. So we have 2 more environments. One of them runs out of battery. This is definitely something it would be great to have even more endurance. So in all cases, it could find the successfully localized gas source. And this is an empty environment with some sort of unit test to see if it also works there. This is an example of the gas traces over time on the system. You can see one agent finds the gas and the others slowly move towards the source as well. You can see here that there's more gas detected by the evolved parameters than the manual parameters. So the evolved parameters actually work in real life. Some of the key findings are that evolved parameters using doping detect more in average gas than the manual parameters, and that they're safer around obstacles. Some problems with them are that if there's downwash when the agents are close to each other, it's just something we didn't incorporate into the simulation. So we cannot really deal with that at the moment. But with this, we validate ultimate TDM because we've learned this parameters in simulation, and now we show that it works in real life. Concluding this presentation, we've contributed AutoGDM, which is the first gas dispersion modeling pipeline, and we hope it allows for future benchmarking. We've contributed a novel computationally efficient bug algorithm, SniffyBug, and it shows that the default parameters outperform the manual parameters. And with that, we conclude the first fully autonomous swarm of gas seeking and quad peppers. The future work is we hope to use it in the larger environments with better sensors, maybe with end-to-end reinforcement learning of some network, or with an improved bug algorithm. So that's it. Yeah, thank you for attending this talk. There are some useful links. The code should be online, the papers online or archived. Yeah, thank you.
Yeah, thank you, Bart, for this really awesome work and presentation of course. All right. Are there any questions? Please put them in the chat. And in the meantime, I do have a question for you, Bart. Do you think that adding, for instance, like the AI deck for some more computational power would have probably perhaps improve the results even more? Or
Um,
what do you think about that?
I think there's an algorithm and a hardware perspective. Like the hardware perspective is that probably if we would have ultra wideband gas sensor AI deck, flow deck, and multi-ranger, then maybe the weight gets a little high. But I think from the what would be very useful with the AI deck is to detect walls better. So if you only have one point with the laser ranger, you basically have no idea if it's like a very narrow pole or if there's a massive wall ahead of you. And I think that information is very useful. So maybe with the AI decks you can like some cool optic flow stuff. That would be very cool.
All right.
There's a question in the chat, right?
Yeah, let me just say it out loud so it's on the recording.
Yeah.
Tobias is asking, how would the size of the drone affect the performance, like the airflow, which might be a bad thing?
That's actually very interesting because I remember some meetings with Guido at the start of this project, and I looked into papers that said, there's no way to send gas on these tiny drones because the airflow gets rid of all of the gas. And Guido said, no, it will be fine. They just put the gas source below the drone. So yeah, and I think that there's certain cases where they cannot smell it, but I think it would be indeed interesting to study the impact of larger or smaller drones on the airflow, basically. But I think we haven't really quantified this, basically. But there's some studies that said that it could be a role, indeed.
All right. There's an other question. What would you think that a reinforcement learning based solution will be better compared to a bug algorithm?
That's also interesting. We've sort of, by designing these rules, we sort of constrain that what the system can learn. So I think there could be a more optimal solution, just because of the constraints that we as humans put into the system. So I think possibly there could be a more optimal solution. That's it. That's it.
All right. I think it will be good to conclude it because there's also a Meet the Speaker Mibo room open in rooms networking and Meet the Speakers Town Hall. So if you want to talk to the speakers face to face, please go there. I hope that Guido's internet will be able to handle it.